In this video, we talk about elastomeric pressure vessels, which are pressure vessels that expand enough that we cannot use the original radius and thickness to estimate what stress will occur when we expose them to a given pressure. To do this, we'll combine Hooke's law with Laplace's law in order to predict what happens under stress. To start our discussion of elastomeric pressure vessels, we'll review what we learned about pressure vessels. We learned these equations for stress as a function of the radius and thickness, and we learned these applied when the radius is much greater than the thickness. And also, in order to derive these, we needed to know the current geometry. And by the current geometry, I mean the geometry under pressure. There's a number of situations we learned that would allow us to know the current geometry. One is, this is what might have been measured directly. It's certainly possible to measure the geometry under pressure with certain imaging tools, maybe not as easy as to learn to measure it in when it's not stressed, where you can actually cut it and see cross sections. It's also possible to know the unstressed size, which we refer to as R naught and T naught. And if we know the material is rigid, that is, the maximum strains must be small before failure, that we can use R naught and T naught as an estimate of R and T. And finally, we might know the unstressed size, R naught and T naught, and we don't know anything about what the stiffness is, or we don't know what the maximum strain is, but we might be able to calculate that given the conditions, the deformations are small. That is, the strains are maybe less than 1%. That will usually give an accuracy of around 2 significant figures, which is generally acceptable. So it might be it's an elastomeric vessel, which could have large strains, but under the given pressure, it doesn't. So these are all situations where we know R and T well enough to apply Laplace's law. But what do we do when we only know the initial radius and thickness, and we expect to see large deformations, so we cannot assume the small deformations, nor do we know the actual radius? So we'll walk through this situation first for cylindrical pressure vessels. So let's assume here that the material, while it's undergoing large deformations, it's within the range of linear elasticity. That is, the deformations aren't that large because we do always leave the linear regime as we go into larger strains. So in this situation, Hooke's law, equations for the stress in the circumferential direction, which can be used to see the change in radius, and the stress in the thickness direction, which can be used to tell the difference in thickness. And each of these are given in terms of the stresses determined by Laplace's law. Laplace's law also tells us that the longitudinal stress is half the circumferential stress in pressure vessels, and that the thickness stress is 0. So we can plug that information into the equations above in order to get expressions for the strain in both the circumferential and thickness directions in terms of the circumferential stress. So these equations are effectively a form of Hooke's law specific for the state of stress that occurs in cylindrical pressure vessels, except that we don't know the magnitude of the stress and strain. Now, meanwhile, regardless of material properties, Laplace's law tells us how to find circumferential stress as a function of the strains, because we can simply define the radius and thickness in terms of the strains and the initial geometry. So we therefore have Laplace's law for stress here in terms of strain, and we also have equations for the strain in terms of the stress. We resolve this circular logic by solving the two equations simultaneously by plugging in these expressions for strain for their counterparts in Laplace's equation. And that results in this equation, which is Laplace's law for pressure vessels with moderately large deformation, assuming Hooke's law. So we can then take this and rearrange it to get a quadratic equation. Take this side, multiply it by that side. We get this, then we subtract this side from both sides in order to get 0 on one side. And we multiply this out to get these two terms. Meanwhile, we multiply out the PR naught over T naught from up here to get these two terms. And then we just group to get terms in stress squared, terms in stress, and then the scalar terms. And we can solve this in two ways. These are a quadratic equation. So we can use the quadratic solution to say that the stress is negative b plus or minus the square root of b squared minus 4ac over 2a. And then take the values of a, b, and c from the cofactors in the equation above. So this is a very complicated formula if you plug all of this in, but it provides you an expression for sigma c. So from sigma c, we can then calculate sigma L, the longitudinal stress, is half the circumferential stress. And then knowing both of these stresses can also allow us to calculate the deformation with Hooke's law in the form we had on the previous slide. So when we do this, it should be noted that we assumed Hooke's law in 3D, but Hooke's law in 1D or 3 doesn't apply for really large deformations because no material remains linear. They become nonlinear for larger deformations. So it's likely that this might apply to strains less than 10 to 20%, and this is needed for strains of greater than 1 to 2% because above those strains, Laplace's law, using the actual radius as we first derived it, are not sufficient if you only know the initial radius and thickness. For spherical pressure vessels, we can repeat this entire derivation because this one only addressed cylindrical vessels because early on in the derivation we used the fact that sigma L was equal to sigma C over 2 when we were talking about the lateral deformation. So we are calculating the change of radius here, but we had to know the stress that was perpendicular to this. Whereas for spherical pressure vessels, we have to use a different fact. We will say that we are calculating for sigma and that the lateral stress is the same. And so that will give a different calculation, knowing that the lateral stress is twice the value it would be in cylindrical vessels when calculating for the radial direction. This is left as an exercise because it's a straightforward set of calculations given the process shown in this video. So this video derives expressions for stress and strain in cylindrical pressure vessels when we only know the initial geometry and we know what pressure it will be under. In the next video, we'll use these equations to understand the behavior of elastomeric pressure vessels as they start to expand in size.